Hello students, this is the next video for the Advanced GIS 1 Teach by Appointment class. Picking up where we last left off, if you remember, our goal was to explore the various ways that you move from nothing to actually having a piece of spatial data in ArcGIS. And in order to simplify that, we went through a couple of major categories. We said data could be downloaded as it is. We all love that one. Someone else prepares the data for you. All you got to do is go get it. We learned that we can join two pieces of data. So that's similar to this component, right? Maybe someone has already made a shapefile of census tracts or counties or zip codes in the United States of America. And then what you do is go and find or create some data, from that. So you may be in your Excel, take all of the states and you write down the number of people that have enrolled for Obamacare in those states, right? So you've got that existing on a piece of paper, on an Excel document, and in ArcGIS you have an actual layer of the states, and you can join those two together. Then we started talking about how you can take things that exist on paper or in an Excel document and get there to be points that represent them in the world. And the two we talked about are the XY coordinate, obviously being the best because you know exactly where you are in the world. And then the one we're probably most familiar with because of Google, if you have an address, you can build something called an address locator, which tells you exactly where that should be located based on a series of home addresses or street addresses or zip codes. So we're moving on to the fifth one now, and these ones could almost each be covered in their own video, but this is going to take a couple to really walk through. Right, we're past the point where we're taking data from paper or by someone else's creation, and we're actually going to build it from scratch. Right, this is on the seventh day God created type business. We're going from nothing here in ArcGIS, and we're going to have a shape, to our choosing. But in order to do that, we have to kind of back up a little bit and really understand what different components spatial data actually has. Right? And I think for the purposes of this assignment, we can really break it down to three primary elements that spatial data has. And when I say an element that a spatial data has, let me show you real quick. If you were to go into just your regular desktop, and this would look differently on yours if you're using Windows, and you were to find the folder, we're working in TBA session B today, you'll be finding that folder. And we have some stuff here on projections, somewhere, there we go, right? There's some projections, and there you go, we got some Philadelphia bad, Philadelphia correct. It makes it look like we've got 30 or 40 different pieces of data in here, but remember, everything here that shares the name Philadelphia correct is part of that shapefile. It is simply that a shapefile has a series of component parts. And that's what we're going to focus on today, is really three that you need to know in order to make your shapefile. One, and what we'll cover first, it needs to know where it is in the world and what it's supposed to look like. Right? Those two are sometimes synonymous, but they don't always have to be. Right? You can have a location based on where you are in the world in Philadelphia. You can have an XY coordinate. But depending on the type of map you're going to create, you can shape Philadelphia in any number of ways to prove your point. That's the problem when you move from a three-dimensional surface to a two-dimensional plane. The shape, we also need to know what shape something is. Is it a point, is it a line, or is it a polygon? And if it's a polygon, what's the exact outline? And then finally, what attributes does it have? Right, so those three things in combination are going to be really what we need to explore before we actually get into creating pieces of data. And so we'll start probably with one of the ones that's the most challenging to wrap our heads around, and I've got some resources here to talk you through it, and that is coordinate systems and projections. Right, so this presentation will be available for everybody, but let's walk through it together. Really, if you want to break it down to as simple as you can, a coordinate system will tell you two things, and that'll depend on whether it's a geographic one or a projected, which is both projections and geographic. So either you just get geographic or you get a projection, which is both. The geographic coordinate system will tell you where you are in the world. Right? Simplifying it, it takes wherever the central datum of the Earth is, and you're measuring out a series of angles that put you on lines of longitude. Right? Those are the x1s that go here, and latitude, those that go north and south here. Right? And so that is how you know where you are in the world. Either you're a point, you're a series of points, that makes you a line, or you're even more points, like 10 of them, and they're connected and you're a polygon. But the purpose of this is it's the mathematical system which defines what coordinate systems tell you where you are in the world. So that's great, but most of the things that we're going to do in Arc, or in GRASS, or in Q, or in any of your GIS platforms require us to switch to a Cartesian coordinate system, right? We need to stop thinking of the world as in three-dimensional space and think of it in two-dimensional space. That's what allows us to create angular measurements, in units like feet, in meters, or measure the area of something, right? Or check out what density looks like, or measure distance to and from 2 points. But everything gets complicated when we move from this three-dimensional space to a two-dimensional space, right? And if you pause for a moment and think about why that is, the metaphor that's always given is to try to take like an orange, or maybe in this point we'll say it's a grapefruit. Imagine someone grew the biggest grapefruit you can imagine. This thing is maybe like the size of an exercise ball. And someone asks you to take that huge grapefruit and peel it, and then lay it out flat. So if you take the grapefruit and peel it and lay it out flat, what will likely happen, as you can surmise, is that you'll rip the edges. Right? Notice that about the world. It is fatter here around the equator than it is near the poles. A two-dimensional map doesn't look like that. A two-dimensional map treats, or most two-dimensional maps rather, treat all space equally. And so what you get are these inflated systems where Greenland looks like it's enormous. Right? Alaska appears to be the size of the entire continental United States of America, and Antarctica appears to just be this enormous, endless mass of snow in the south. Really what's happened here is we've made choices in how we want to project, how we want to move from 3 dimensions to 2 dimensions, and certain things are going to be preserved, direction, area, distortion, but certain things are actually going to be harmed in doing this. In terms of projection basics, when we begin in a 3-dimensional space, a couple of big terms that you'll hear often are like planar, conic, and cylindrical. And I'm offering this graphic to help you think that when you project something, right, the other metaphor that's given is imagine if we had a light bulb inside of this. And this was translucent, and we put a piece of paper around it in one of these 3 fashions, and then you turn the light bulb off. Well, an image would get projected in one of 3 ways. If you're a planar, right, what you are is that you're tangential to the world at some point, right? You're coming off of it, hitting it and touching it at one point here, and so the light would shine through that point, and you'd be very, very accurate in your shape and your size and so on and so forth for that point, right? But you're not going to be able to see anything else in the world, right? Look at this little shape here. The light's coming through. All you really get is that kind of circular part where it touches. Conical is another form, right, in which you're preserving maybe, a hemisphere or one section of the Earth, but you wouldn't be able to see beyond it. And cylindrical is the final one in which, yeah, you likely are shining light and you're seeing the entire world, but because you're trying to take the world and make it flat, you get these distortions up here at the edge. Some general terms that you'll see when you're looking at how you project something. And again, I'm starting theoretical here for you. And after this, we're going to get very, very practical. There are going to be some students that find this fascinating, that want to dive into the mathematics behind it, and I'll provide some resources for those students. And there's going to be others of you that say, Shay, just tell me what I need to make sure I'm working in here. So we'll be able to cover both students. So some general rules, there's properties, right? And the properties are trying to define the activities you're going to use the map for here, right? Is this conformality? Are you trying to make sure that all points, preserve their distance? You're trying to make sure everything prefers their shape. How much space do you want to map, right? That's kind of the thing that we've shown here, right? Do I want to map, the whole world? Do I want to just map a hemisphere? Do I want to just map maybe like a plane of some kind? how am I putting it on the map, right? Am I covering everything? Am I going north-south? Am I going east-west? And, how am I kind of touching, really, right? Is it hitting at a tangent or is it hitting at a secant? For practical purposes, though, things end up looking like this, right? So just to give you an example, these are four projected coordinate systems or four coordinate systems. Mercator, which is those of you who use Google will be familiar with this, right? This is what we're seeing here. It's the most commonly used projected coordinate system to display the world in. And, that sometimes has the benefit of everybody being able to recognize it, but Mercator has some serious flaws. As you can tell, it really, it narrows down things that are closer to the equator, and the farther you get away from the equator, the larger things tend to look. So this is one of the reasons you probably grew up thinking that Greenland, Alaska, and Antarctica were enormous when really they're not that big. All right. Universe, this is actually totally another one. This would be taking the root of Mercator, but let's say we projected ourselves for just one area, and this is the UTM Zone 11. We'll check this out a little bit later, but you can see the world starts to shift because we're trying to focus in on a small, just one little area. And you got the World Geological Survey here, and then you have the one here that likely looks the most familiar to you. And it's not necessarily that it's right, and that the others are wrong. Every single one of these is correct given the rules of the projected coordinate system. It's simply that this tends to be the way the United States of America, or the continental United States, is presented to us in atlases, right? We recognize that small curvature that we see here. The shapes look in excellent proportion to each other. So just something to keep in mind, that when you're making a map for someone, we'll review this in ARC in a minute, that how you choose to project the world is going to impact how your users see and interpret your map. So as I said, for practical purposes, we will almost never work outside of this coordinate system. The state plane coordinate system is something designed for the United States of America. And what it does is it's a series of, 50, or actually way more than that, around 100 individual elements of one larger state plane coordinate system, and each element gets a code that defines a certain area, right? So if you're working in North Dakota, and you know that you're working in the northern section of North Dakota, this is your coordinate system that you would use, right? This coordinate system is meant to preserve shape, distance, and proportion over small distances, right? So because of the shape of the states, right, whether they're north, south, east, west, the size of them, the angle, cartographers have been able to create coordinate systems that work within those, those unique considerations of shape. So what you get is that when you're working in an area like where we are in Pennsylvania, using this coordinate system will give you that shape of Pennsylvania that you recognize. It's almost like it conforms the entire world to accommodate this one part of the world. And so a state plane coordinate system is excellent when you are working in those smaller areas, which is really what we're going to do in this class, right? This class is about landscape architecture. This class is about suitability and sustainability, right? This is about demographics in a city. You're rarely ever going to be working at a scale where you might need to show the world or the United States, but that's why I've provided some of these resources. So if you ever do need to pop up to the US, right, this tends to be the coordinate system people recognize. Just another way to help people, think through whether the zones move in a more north-south direction or an east-west based on the shape of the state. The only other one you might see us use occasionally is what's called UTM, or Universal Transverse Mercator, right, which essentially splits the world into a series of kind of north-south grids and east-west grids such as this. And then based on where you are, that's the projection. So remember we showed UTM 11 as one example here. Right, that's what's happening. If you picture UTM 11 really being this kind of western part here that goes through Nevada and Idaho and the eastern part of Oregon and Washington, right, in order to project and show and preserve distances and shapes and angles in that area, the rest of the world and the rest of the United States would be kind of tainted, right? So when you're looking at a state plane or you're looking at universal transverse Mercator, you are looking over a short area, right? You are looking at a specific city, a specific state. You're not meant to be mapping at a much larger area. We're going to dive into ARC in a minute just to show some examples of that, right? But for students who find what we've talked about here a little bit fascinating, what I wanted to do is be able to provide some links to you to be able to explore it a little bit more. So you're going to get this on your sent to your email, and it's just a number of really cool ways that people from ESRI or other people have created graphics and visuals, right, that allow you to play around with your projection wizard. Right? Like you can pick whether something should be equidistant or compromised and where it should be in the world, and you can see the various examples, right, of what the world might look like when you do that. Here's another cool one that shows an animation, right, of how the world shifts based on your projections. And then a really cool one that's similar here, right? You can pick the world you want, and you can see how you'd shift, right, at various areas and how the world would become distorted. But for now, let's move past these and let's actually head into ArcGIS. Right, so I've got a couple of things here. So here I've got one that I've called Philadelphia Weird Shape. And within that is Philadelphia Correct, and then something called State No Projection National. And if you're looking at this, those who've worked with Philadelphia before are going to look at something like this and say to themselves, you know, this just doesn't look right, right? Philadelphia maybe looks a little bit less like it's moving on that like north and south axis. It looks a little bit more almost like a diagonal than it usually does. Contrast it with here, right? And I was able to create multiple data frames by going to Insert Data Frame. And I'm going to right-click here and I'm going to go Activate. And now suddenly we're seeing a Philadelphia that is much more recognizable. Again, neither one of these is correct, right? Or perfect would be the better example. It's just one is a little bit more correct than the other, right? Because it preserves units of distance, shape, distortion that would work for modeling Philadelphia. So when you're working in ArcGIS, something I want you to remain apprised of, this is a data frame. Data frame, data frame, data frame, data frame. A data frame is composed of layers, layer, layer, layer. The data frame itself will have one overarching coordinate system that it's using to project all of the layers, but each layer can have its own as well. Rarely will you be in a case where those two come into conflict, but sometimes you might. In order to understand something's coordinate system, you right-click and go to Properties. Go to Source, and that's where you're able to see. So right here, Philadelphia should be working for us, right? Okay, it's a projected coordinate system. I can see that it is the state plane that we had talked about. Right? It's projecting itself in feet. That's the unit of measurement, and I can see that. This is where it's supposed to be in the world, how the angular units are measured by degrees, but for some reason it doesn't look like it does here, right, where the same thing is the case. If I go in here and I look at its properties, there you go, I can see that it should be working. So what that means is that the coordinate system of the data frame, notice what I'm doing here, I'm clicking on the data frame and I'm going to its properties. It is not projected, right? The coordinate system here is just a geographic one, and I can tell that because there is nothing that says projected, right? Notice, I go in here, projected coordinate system. There is some mathematical equation going on to take this from 3D and put it in 2D. Here there is not. And so what happens is you get what's called an on-the-fly projection, right, where it visually pretends like it's projecting, but there really isn't one that's defined here. And in order to help you understand this a little bit more, I'm going to jump ahead real quick to the one that says totally blank. And I'm going to help you understand with totally blank, there is no coordinate system right now because nothing has been brought in. And I want to do an experiment. I'm going to grab Philadelphia Correct and I'm going to drag it in. It's going to look correct. And then I'm going to come up here and I'm going to see that in fact the coordinate system for the data frame is a projected state plane. So using your powers of induction here, I want you to realize that whatever layer comes in first does what's called priming the data frame. It sets the coordinate system for the data frame. It determines what your world is going to look like. If you didn't actually want that, right? If you were like, oh God, no, I eventually want to be showing this at a world scale, right? Or at a United States scale. I'll bring in my, where am I going here? Yeah, right. Oh God, I don't want to show it like this. I eventually want to be like, zooming out, because look what happens when you zoom out if you're at the state plane coordinate system for Philadelphia. Right, just like I showed you. Oh my goodness, right? The world is literally tilting on its axis so that we can show Philadelphia. And you can imagine how crazy this would be if I had the rest of the continents on here. Maybe I do. I'll just drag in the world at the bottom of it. Right, we can see what we've done by preferring Philadelphia over the rest of the world. The whole world has shifted on its axis to prefer Philadelphia. Right? It's even been able to cut China and Russia in half here because it can't show them. So what I'm saying to you here, though, is let's say you got yourself in a situation and you're like, this is not how I want to show the world, right, in any capacity. It's not what I want to do. I want to show the United States in that system that I'm used to measuring it. You can change this at any moment, right? So you could come up here, and under coordinate system, you're going to get a couple of choices here. You're going to get to pick by browsing. Right, a projected means that there's some system going on here that's going to use mathematics to determine three-dimensional space. If you're ever using a geographic coordinate system, the only reason you ever would be is if it's all about kind of the angular measurements and what the degrees should be measured in. And if you're doing that, you're usually going to be in North America, and you're going to be working in NAD 1983. Right, but for these purposes, I want to define that coordinate system, that makes the world look like the world. So I could go to continental North America, come on down to U.S. National Geographic Atlas, and I can apply it. Yes. And right, the data itself, nothing's happening to the data. It's simply projecting the world in such a way that my shapes are conforming from a visual perspective to that coordinate system, right? So here, the projected coordinate system of the data itself still might not exist. But I've projected the data frame in such a way. So right now, it's totally visual. There's nothing analytical. It's completely visual about what's happening. There are other ways to model your coordinate systems, right? You're not going to be at a point necessarily where you can remember, how this is supposed to work, right? Projected, and then there's state plane. And then there's state plane, NAD 1983 feet, and then you got to find your specific state plane coordinate system. I mean, eventually you'll build the muscle memory to be able to do this. But until that point, there's another cool way to do it, and it's through here by adding a coordinate system through what's called import. So this is hiding. You might never see this, but it's important to remember. If you know that some other piece of data has the right coordinate system, you can find it and take it on. And we'll show that as an example in a second. So I'm going to come back to my one of the nice shaped Philadelphia. And I have this thing I called Philadelphia bad. And I'm going to drag it in. And I know that it's bad because I screwed up its coordinate system. And as I keep coming out, I can't find this Philadelphia. It's not showing up where it should be. And if I right click and I zoom to it, I mean, it's in like a weird area. I'm not even sure where it is in the world. I zoom out, and I can maybe see. Somehow this coordinate system has placed itself. Where have I gone? I've zoomed out too much. What have I done, students? Zoom in a little more. Find yourself. There we go. It somehow placed itself on the border of Carolina, almost Tennessee, and Georgia. Right, so its coordinate system has been totally messed up. So there's a couple ways you can repair a coordinate system. You can go right to the source. Like I could come in here and go to its properties. There's the problem, right? I've given it a state plane coordinate system for Tennessee, I should switch it back to what it is here for Pennsylvania. If you don't memorize what it is, that's where this cool import comes in handy that I taught you. You could tell yourself, well, wait a minute, I know for a fact that Philadelphia correct is the right coordinate system. And it would then take on that coordinate system. And I'm not going to do it in here because I want to show you another way. So that's one way. You can go right to the source in catalog and you can import the correct coordinate system. The other way is if your data frame is in, and I'm sorry to repeat myself and sound ridiculous, but I really want to build that in, that a data frame could have a different coordinate system as a layer. If the data frame's coordinate system is correct, you can export and have it take on those properties. So if I export bad, right-click, data, export, use the same coordinate system as, well, me, or no, use the same coordinate system as the data frame. And then what you're able to do, and I'm just going to save it here in a random file here, is it will take on the correct coordinate system, or what we know is correct here because it's the frame. And then let's scroll up, and hopefully everything worked out, right? Oh, nope, still did not. So that's interesting. So from this one, it did take on the correct coordinate system, and let's see what happened here. This is actually pretty interesting. Aha, so what's happened here, and I'm glad actually that this occurred, right? So there's Philadelphia fixed. Here's Philadelphia bad. Right, so we did export it with the correct coordinate system, but the problem came, if we look right here, is up here, right? So its extent, it's still keeping the same extent that would shape it in this part of the world. Whereas Philadelphia correct, if I drag that one in, feature extent, it's a much different extent, right? So we need to get the proper extent. And so really one of the best ways to go about that is just to change it directly in here, right? So let's go to XY coordinate system, Philadelphia bad, you should be Pennsylvania. Right now we drag in Philadelphia bad and it's okay, right? It's exactly where it should be up here. Cool. All right, so that's how you're projecting things. You can export it, you can fix it directly in here, or you can go up to a tool under data frame, data management, projections, transformations, and you can take care of it here.